Hello everybody, Greg is here. Today I want to talk about this beautiful new molecule which was published in February 2023 by those co-authors. One of the reasons I enjoyed reading this paper is because I'm coming from the field of silicon chemistry myself, but don't tell anyone. You can see here that the molecule on the picture looks like a pyramid, and the pyramids are what the authors compare it to. My first thought was that it can be rather described as a silicon apple on a square carbon plate, but we'll discuss that in the end of this video. So why is this molecule so interesting and unusual? First of all, you see the silicon here? This is completely not normal situation. Normal situation for silicon is to be something like this. So it has 4 bonds which are all look in different directions. Like in carbon, silicon is located under carbon in the periodic table. You can see these 4 bonds arranged in completely different ways. Second unusual thing, you can see those 2 dots here, that's free electron pair, which can react with different molecules. That means those 2 electrons do not participate in those 4 bonds. Basically, those 4 bonds are formed by 2 electrons from silicon and 4 electrons from the carbon square. As I said, very unusual situation. Also, interestingly, very similar molecules, but instead of silicon, they had the germanium, tin or lead were published before in 2013 and 16. So this molecule, if it just differs by 1 atom, why it was published in one of the most important chemistry journals? So that's what we are going to discuss today. Well, in general, this type of work is one of my favorite because it deals with new type of molecules. For example, if you look in biology, a biologist makes a discovery when he finds a new type of animal or insect or bacteria. These types of discovery is also possible for chemists if they find some new type of material or molecule in nature. But most research of this type goes when the chemists make the new unusual molecule by themselves. So this paper is much more than just this one new molecule. How was it synthesized? Well, to synthesize an unusual molecule, you need to start from another unusual molecule. And this was this one, divalent silicon, silylene, with chlorine and amino ligand, which is stabilized by a coordinative bond with another nitrogen. And my guess is that the authors which had this molecule for already previously, they did some reactions and published some reactions with it. They looked for interesting candidates to react this molecule with. This was candidate because it's a very strained square molecule with double bonds, and silylene is known to react with double bonds, especially if they're so strained. So they just tried to react it with. I'm not sure that they knew what to expect. So that's the reaction and that's the product. So what happened here? As they expected, this silicon with 2 reactive electrons here attached itself to the double bond, but then a 3-methyl-silyl group migrates to another carbon and a double bond between carbon and silicon forms. Now this already an unusual molecule as well. Very unusual because it has a silicon-carbon double bond conjugated with carbon-carbon double bond. Basically it's silapyramidane. And with this arrangement of silicon and carbon atoms, it's the first of its kind. You can see this molecule has chlorine, it has amine, and those atoms, especially when they are on silicon, they're very reactive. You can use a reducing agent to just remove them. And that's what they did on the second step. I forgot to mention, this is the X-ray structure of this molecule. The X-ray crystallography is still the most precise method to identify a chemical structure. So you obtain a crystal, you irradiate it with X-rays. From the diffraction you can identify the repeating unit and the arrangement of atoms in this repeating unit. As I said, the next thing that they wanted to do is they wanted to react this chlorine with something, and they used a reducing agent, a lithium naphthalenide, and look what happens. This pyramid forms. So okay, how it forms. So as I said, the chlorine is removed, but also this whole amine ligand is removed as well. And then a 3-methyl-silyl group migrates back, and this silicon just finds itself on top of this carbon square. And again, we have X-ray structure. Okay, so what's so special about it? When Sekiguchi and Lee got those compounds, they didn't do much chemistry with them. So these guys wanted to improve on that. They took this molecule and tried to react it with other compounds. It has silicon with the pair of electrons, so they reacted with another equivalent of this cyclobutadiene. Indeed, you have the reaction, but not with the double bond, but formally at least with the single bond. Not only with this single bond, but also with the single bond on the square plate here. And this beautiful compound is formed. That's nice, but this reaction I think is even nicer. First of all, because it preserves the structure of the pyramid, and because it's shown that this pyramid can serve as a ligand to a transition metal. It's always good to have new ligands, because transition metal complexes are often catalyzed reactions, and getting new ligands to transition metals can be very useful in the future to fine-tune some catalytic production, a very interesting and important achievement. Here you can see the X-ray structures. You can know if it's a double bond or single bond by the distance between the carbon atoms. And the last but not least, what they did was to do quantum mechanical calculations of the electronic structure or the electron density. And so here you can see cross sections of the pyramid from this carbon to this carbon and from this carbon to this carbon. This electron density on the silicon really corresponds to the lone pair of electrons. It's all calculatable. You can see the critical points of the electron density that correspond to chemical bond between silicon and carbon. Critical point that correspond to a ring. So that's the base ring. And also critical point, the blue one, that corresponds to a pyramid. I don't want to go into what those critical points are. It just shows that the pyramid is likely the correct way to describe this. Although I still feel that the apple on plate looks at least as nice. Thank you for the attention. I hope it was interesting. Please subscribe to this channel and like the video so the YouTube algorithms will share it with more people. And of course, support Ukraine.